These days, you got to have a PhD in engineering to teach at a university.
Wow, and it's only you?
Uh, yeah, I guess it is only me in the electrical. Dr. Curling has it in mechanical and civil. No, he has PhD in mechanical.
So if you go in our degree, I guess our degree program will be basically shut down then.
No. I'm talking about any new hires.
Or new hires.
Yeah. No, you could get you could get accreditation with just somebody in masters at this level. If you're going to teach at a bachelor degree level, somebody with masters will do for accreditation. All right. How many people here? Give me a second. Let me ask this email in case it's relevant to this class. But it's not. Okay. All right. Good morning, students. Folks, thank you very much. One person with some common decency. Okay. Today we want to talk. Last class we talked about. Last class we talked about, and decent students don't interrupt somebody when they're talking. Last class we did FIR design, equal ripple FIR design, but we use software, free software that we found on the internet. Today we want to talk about IIR design, IIR filter design. Okay. And one method we're going to use, there are actually a number of different ways of doing this. One method is bilinear transform. Bilinear transform. Another method is impulse invariance. Wait a minute. How did I get suddenly get 9 people? Oh, one's joining. Okay. We may or may not do the second part. I haven't decided yet. So the bilinear transform. The idea of bilinear transform is to start with an analog filter. Start with, so this is one. Bilinear transform. Okay. Start with, well, in both these cases, start with the analog filter. Okay. E.g., what's that? What is this? Go ahead.
Is it a transfer function?
Of what?
Well, you saw the
First,
bottom.
first order, last bit of Butterworth.
All right. So, in this class we use HA. In my other class we use G. This is HS. The transfer function of a first order Butterworth. Finish it for me.
That's what the cutoff frequency of 1 rod per second.
Yeah, but you haven't told me what kind of filter it is.
Low pass.
Low pass filter with omega C equals 1 rod per second. Good. That's from 410. Okay. So how do we get a cutoff frequency of omega P?
You ask, how can we get the cutoff frequency of omega C?
No, omega P. We want the cutoff frequency of omega P. What do we do to this transfer function?
And with 410, we replace S with S over omega C over omega P.
Yeah, okay. So we can do so 1 over S over omega P plus 1 is omega P S plus omega P. And this is the same thing here. First order Butterworth low pass filter, but now omega C equals omega P. Okay. So the idea of the bilinear transformation is we take this function of S, and where we have S, we replace it with a bilinear transform. And I'm going to go to the next slide. So everybody snip and tell you about the bilinear transform.
Give me 1 minute, boy.
This should really be called design using the bilinear transform. That's a better title. Okay. Everybody got it?
Yes, sir.
So now I'm going to talk about the bilinear transform itself. Okay. The bilinear transform is used where you see S, replace it by a function of Z. Because when you have a function of Z, that'd be the digital filter. So S is going to be 2fs Z minus 1 over Z plus 1. This is a bilinear transform. All right. So this is the relationship between analog frequency, that's J omega. This is J omega over here. And this is actually a function of digital frequency. And I'll show you that now. So this is 2fs. Z is e to j omega minus 1 over e to j omega plus 1. So this is 2fs. E to j omega over 2. E to j omega over 2 minus e to the minus j omega over 2. Okay. And I'm going to I'm going to divide by 2j and multiply by 2j. And why did I do that? Anybody see why I did that? So this is J4FS. No, I ain't done it. And then the bottom, of course, becomes, the bottom becomes either j omega over 2 times either j omega over 2 plus either minus j omega over 2 times 2. So this 2 cancels that 2. So why did I do that? So that cancels that. Why did I do that? Y'all do not study. We just did this last class. Because this is sine omega over 2. And the bottom is cosine omega over 2. Why couldn't you all tell me that? We just did this last class. Therefore, we now have j omega equals j2fs tan omega over 2. So the j cancels the j. So this transformation, okay, takes analog frequency and relates it to digital frequency. When we use the bilinear transform, this is now the relationship. Now, this is not to be confused with. Let me rearrange this. So this is 2 pi f equals 2fs tan omega over 2. So that 2 cancels that 2. Okay. So pi f over fs equals tan omega over 2. This is not to be confused with 2 pi f over fs equals omega. Don't confuse these two. This is the normal relationship between analog frequency and digital frequency. But when we use a bilinear transform, this becomes the relationship. So whenever we use a bilinear transform, we have to think this. Okay? Any questions about that? We know the bottom one. The top one is something new. Don't confuse them. So let's go back to our analog first order low pass filter with cutoff frequency omega p, Butterworth, first order Butterworth. Okay. So this is H of S. To make this H of Z our digital filter, we now do this. Where we have S, replace it with the bilinear transformation. So this is now omega p, Z plus 1 over 2fs, Z minus 1 plus omega p times Z plus 1. So this is omega p, Z plus 1 over 2 fs z plus omega p z minus 2fs plus omega p, or omega p over z plus 1. Okay. 2fs plus omega p times z minus 2fs plus omega p. So now what do we have? We have h of z. This is the transfer function now. This is the transfer function now of our equivalent digital filter. Any questions about that? So here's the analog filter. And here's the corresponding digital filter. Okay.
Dr. Cartwright,
Yes?
I took a picture of the last page, but I didn't see what you wrote. It's one B word. I can't pronounce it, but
Bilinear? You can't pronounce
yeah.
bilinear?
I couldn't remember. Sorry. Now you were saying because the bilinear S became that. Did you define? Did you show that on the last page or no?
Mr. Johnson, what were you doing while explaining all this?
I was looking.
You're looking at what?
Could I see the last page?
You don't have a snip of the last page?
I did take a snip, but I didn't take a snip when you was defining the bilinear. I only took a snip when you had the omega equals to 2fs times omega over 2. I didn't have the other one.
So why did you ask me for a snip? I wrote this whole page 3, and you still asked me about the snip of page 2. What kind of student are you?
Sorry, Dr. Cartwright.
Y'all think y'all could play around, do whatever the hell you want, and then I must comply when I finish another page. I must go back to the previous page.
Thank you.
What is your question about this page?
I okay now.
Okay. Give me a second, please. I don't know why Mr. Anderson's internet is so terrible. He's in his car. That's probably why. All right. So let's do that then. Let's do example of that. Let me get. You can question right out of the book. Right out of the textbook. Let's make it bigger. Wife said. Okay. Here's question. The first order function for a first order, the transfer function for a first order analog low pass filter is described by equation 10 when. They're referring back to omega p over s plus omega p. The filter has negative 3 dB frequency of 2000 rounds per second, which is 318 hertz. Find the transfer function. Find the transfer function, H to Z, for a digital filter that matches this analog filter when we're using the FS equals 1500 hertz. Okay. So we got this analog filter 10.6. Okay. What's the bottom equation? What's the bottom equation?
I know that's the magnitude of something. I know it's not the transfer function because I see it's H omega, something different.
Well, if y'all don't take the time to learn anything, what's the bottom equation, folks?
Bottom equation is the frequency response, right?
Be more specific. It's the magnitude response. Don't you see the magnitude signs? The bottom equation is just the magnitude of 10.8, 10.6. It's just the magnitude. And how many times have we done that? In 320 and 410. Oh. So that's telling me you can't read a book without me. That's what that's telling me. You can't read this textbook without me. So given. This is given. So omega p, the cutoff frequency. Cutoff frequency is 2,000 rounds per second. Or which is same, or FP is 318.3 hertz. Same thing. Also given FS equals 1,500 hertz. From this, the magnitude of that becomes h of omega equals 2,000. The s is replaced by j omega. That's why it's now as a function of omega. Because the s has been replaced by j omega, like you must do when you're taking the frequency response. Okay. And the magnitude of top is 2,000. And what's the magnitude of the bottom? What's the magnitude of the bottom? What is the magnitude of the bottom? All right. I don't know how many.
You don't put the J. You don't put the J.
Thank you very much. The J is never in the magnitude. The J is never in the phase. I just corrected the last homework you all turned in. I just corrected that in almost all of your results, except for 1 or 2 people. And here it is, a lesson later, 2 days later, you all are making the same mistake, which is telling me what? You all only look at your grade, you don't look at the corrections. So I spent all my time correcting your work for no reason. There is never a J in the magnitude. There is never a J in the phase. And by the way, concerning that homework, there was one master sheet and all of you copied from it. And I could tell that by all the silly mistakes every made. They were all the same silly mistakes. Anyway, in the final exam, you ain't gonna have that master sheet. Let's see how you do then. And the final exam is worth 40%. So this is square root of omega squared plus 2,000 squared. We could write that as 2,000 over 2,000 squared times omega squared over 2,000 squared plus 1. So this is 2,000 over 2,000, the square root of omega over 2,000 squared plus 1. 2,000 cancels 2,000, and we left with 1 over square root of omega over 2,000 squared plus 1. There was one student who started in the last assignment. Let's get back to that last assignment. Started giving me just 2 decimal places. And all the copyists used those 2 decimal places, even though it's wrong. No student stopped to think, Dr. Cartwright always, since we've known him, asked for 4 significant figures. Okay. So the first person got it wrong. I think that's Mr. Roll. I think Mr. Roll was the originator of that document, and the rest of you copied from it. Now, if I'm wrong, Mr. Roll, correct me.
I'm not too sure what happened, Dr. Carter.
Excuse me?
Hey, Dr. Carter, I don't too sure what happened with the homework, but
So you deny what I'm saying?
I'm saying I did the homework for me. That's what I'm saying. Everyone
Well, you only gave me 2 decimal places too?
I think at first I did, and then you sent out the email, then I changed everything to how you like it for significant figures.
Yes, but the original document is the one that was circulated. And the sheep just followed that document. And none of the sheep said to the shepherd, this can't be right. Anyway, I don't worry too much about those individual homeworks, because they only worth 30. The homework is worth 30%. The tests are worth 11%. You got to write the final exam, and then we'll see how well the sheep do. I'm showing you how the magnitude given in the book just comes from the magnitude of the transfer function. Nothing new there. We're calculating the magnitude of the analog filter because we want to compare it to the magnitude of the digital filter that we will design momentarily. And while I think of it, the magnitude of E to J omega, the magnitude of this is always 1. Always. Not 0.997. And you can prove that easily. Because this is the magnitude of cosine omega plus J sine omega. So that's square root real part squared and imaginary part squared. And from math, cosine squared plus sine squared equals 1. Square root of 1, which is 1. And not one of you, well, I can't remember what Mr. Beauchamp did. Mr. Beauchamp had no part of this. Mr. Beauchamp did his own. Not one of you considered that possibility. Not one of you. And by the way, it doesn't matter whether it's E to J omega or it's E to minus J omega. The magnitude is still 1. But when you do your assignments, you don't think. You're just happy somebody came up with a solution and you grabbed onto it. I'm looking forward to the final exam. I hope you are. Let me go back and repeat what I was doing before I took off on this path. We're given a transfer function. First order, Butterworth low pass filter. Cutoff frequency of 318.3 hertz. That transfer function has a magnitude. And the book gives it as this. But that's the same old magnitude we know.
Dr. Cartwright,
Yes, go ahead.
I have a question like for the exam or for future references. I know for me, I normally stop at this point where it's say 2000 over square root of omega squared plus 2000 squared. Are you required to go all the way down to this part you just circled?
For this problem, no. But what you may or may not remember, we did it. We did it in 410. Is the magnitude of the nth order. An nth order, the magnitude, okay, of a Butterworth, okay, nth order is simply 1 over root omega over omega c to the power of 2n plus 1. See, this is first order, so that's 2. So that's why they put it in this form. Because the Butterworth has a simple magnitude. It has a formula for magnitude. You give me the order, a second order Butterworth. This will be the magnitude where this exponent now is 4. That's why they put it in that form. Any other questions? Again, we did that in 410. Let's get back to this question. We have the transfer function, analog transfer function. We have the magnitude of that transfer function. Because we're going to want to plot the analog magnitude compare it to the magnitude of the digital that we derive, the digital filter. So I'm going to the next page. I hope you all had a chance to have a snip. Speak now, if forever hold your peace.
1 minute.
Again, you are always the last person to get snips.
Thank you, Dr. Cartwright.
Cartwright,
Yes?
you're saying something about that magnitude of e to the j omega. That would always be 1.
Yes?
And we had
You-
that. Yeah,
Yeah?
yeah. We had that recently. Yeah.
You had it in the last the homework you just turned in. You don't know because you just copied blindly.
No. I copy that.
Young man, you had e to the j 1.8.
Yes.
Well, how's that different from what I just had?
We converted first before we went to the magnitude.
Why does that matter?
I was just saying.
So you converted to cosine 1.8 plus j sine 1.8, except that I think you all used the negative. All of y'all used the negative. There was no need to go to the negative. But all of y'all did it. You went to the denominator and turned it into positive, sorry. Yes, you went to the denominator. It was negative on the numerator, and all of y'all went to the bottom and made it positive.
Yeah.
Yeah, and there was no need to do it. And all of you did it. All of you did it because the first person did it. And then you get this. And then you get this. And then you give me this answer in 2 decimal places, 0.22 or 0.23.
Question. So we didn't have to like put it at the numerator. I mean, out the like how we switched it from negative to positive. We could have just leave it positive and just work with it like that.
No, it was on top and it was negative on top.
Yeah. So if it was positive on top, we could just leave it like that.
You can leave, if it was negative also, you could just leave it like that. If this is negative here, then this becomes negative here. That's the only change.
Okay.
Any other questions? Okay. So now we make H of Z. And how do we make H of Z? Right. We take H of S and set S equals 2fs Z minus 1 over Z plus 1. That's how we make H of Z. So 2fs in this case is 3,000 hertz. Right. So we have 2,000 over S plus 2,000. Evaluated at S equals 3,000. Z minus 1 over Z plus 1. So we make that substitution 2,000 over 3,000. Z minus 1 over Z plus 1 plus 2,000. Okay. And the first thing we can do is divide top and bottom by 3,000. So top becomes 2/3. Okay, and Z negative 1 was Z plus 1 plus 2/3. And so this is 2/3 times Z plus 1 over Z minus 1 plus 2/3 Z plus 1. And so this is 2/3 z plus 1 over 1 plus 2/3. That's 5/3 z. That's 5/3 z. Okay. Minus 1 plus 2/3 minus 1/3. Okay. And we want this in standard form, so we want this 5/3. So we divide top and bottom by 5/3. So that becomes 2/5 z plus 1 over z minus 1/5, or converted to decimal, 0.4 times z plus 1, okay, over z minus 0.2. There's our filter. There's our first order digital filter. First order digital filter. Any questions about that? So we start off with analog filter and we end up with a digital filter. Now, how good is this filter? So clearly now we need the magnitude response. We need the magnitude response of this filter to see if indeed we have a cutoff frequency. We have a cutoff frequency of 318 hertz. How do we get the magnitude response of this filter? First of all, go on to the next slide. Take a snip. How do we get the frequency response, the magnitude of this filter? So h of z then, h of z is 0.4 z plus 1 over z minus 0.2. That's standard form. How do we get the magnitude of the frequency response?
Dot and because all them are real numbers, wouldn't the magnitude be 0?
Mr. Johnson, what you just said now is pure nonsense.
All right.
Why do you think z is a real number? What is the value of z?
Oh yeah, that's e to the power negative j omega.
No, it's e to the power j omega. Where you get negative from?
Sorry. I guess the first thing we can do is expand the 0.4 times.
To get the magnitude, we need the frequency response, h of omega. So that's point e to j omega plus 1 over e to j omega minus 0.2. And by the way, I don't know when y'all gonna learn this stuff. I don't know when y'all think y'all gonna have time to learn this stuff. So now we want the magnitude of this. we want the magnitude of this, so this is 0.4 cosine omega plus 1 plus j sine omega. The bottom is cosine omega minus 0.2 plus j sine omega. And so we have the magnitude. Okay. So the magnitude of the top becomes, what's the magnitude of top?
That'd be 0.4 cosine omega plus 0.4 plus 0.4 j sine omega.
The square
That's-
root. Yeah, the square root.
I just finished telling you all there ain't no freaking j in the magnitude. I just finished telling you all that.
I know, but I wasn't sure if you wanted to skip the step of expanding the.
You can't skip the step because you're saying magnitude equals.
No, what I'm trying to say is before we get to doing the square root, I didn't know y'all was jumping it up out there.
Well, man, you would have had to tell me if what you're saying is true. You would have had to tell me the magnitude of. If you're gonna leave j in this numerator, you're gonna have to put magnitude out here in front.
Yes, sir.
We could skip that step, right? Or
Yes, you can. Yes, you can. I thought that's what he was doing. But only after the fact I tell him he was wrong, then he tried to cover his ass. Mr. Duchamp, please give it to me before my high blood sugar kills me.
So I was gonna start it off with the square root. Square root of 0.4 cosine omega.
No. 0.4 times the square root.
Yeah.
Yes, go ahead.
That's cosine omega plus 1 all squared. Plus sine omega squared.
What's the bottom?
Now the bottom is the square root of cosine omega minus 0.2 all squared. Plus sine omega squared.
That's the magnitude. And that's what we plot. But we haven't plotted. We have to plot it not versus omega. We're going to have to plot it versus f. Why? Because I want to compare it to the analog. I want to compare it to the analog. So how do I change this omega to f? So the magnitude of h of f now is what? What did I do? How do I make that omega f? And this is a digital. What's the relationship between digital frequency and analog frequency?
We need to give it us in the previous speed. I think it was 2 pi f over fs equal omega.
Omega equals 2 pi f over fs. And f is 1500. So wherever you see omega, that's what you put. So I'm not going to write that out. Let's do that in octave real quick. I'm running out of time here, but anyway. So edit bilinear transform. Well, let's do the whole title, filter. LPF filter with bilinear.
Show on your screen?
Oh, I guess not. I'm sorry. Give me a second. Edit low pass filter with bilinear. By then what happened? Dot M. Well, I guess I could put transform in. Yes, I want to create it. Okay, so y'all tell me, what are we gonna do? I want to plot two things. I want to plot the analog, the magnitude of the analog, and I want to plot the magnitude of the digital. So what am I gonna do? How am I gonna do this? Y'all don't know how to plot a graph?
I guess what you could do, you could define what omega is.
You talking about analog omega? What omega are you talking about?
I'm too sure. I got a lot.
All right, let me help you out. I want to plot the analog filter, the magnitude of the analog filter. Help me out. What's my x-axis?
Would you start off like x equal 10?
X equals 10? What do you call an x? Young man, what's the x-axis called? You're trying to plot a graph. You're trying to plot the magnitude of the analog filter. What is on the x-axis? Okay, I see. I see your next assignment, your next task involve octave plotting. So one person can figure it out and the rest of you can copy from it. What is on the x-axis, folks?
0 and pi.
0 and pi. See, I even ask you what is the range. I didn't ask you what is the range. I asked you, what do you have on the x-axis?
Uh, the wave frequency on the x-axis.
Frequency and what unit?
Hertz.
Hertz, yes. So therefore we need multiple values of f on the x-axis.
Yes.
F equals 0. 0.01. What's the highest value I need?
Pi.
Really? Pi is in hertz? Really?
Sorry.
What frequency does pi correspond to?
Digital.
Excuse me? What hertz does pi rise correspond to?
$3.14.
Yo, man, all you gave me is, instead of saying pi, you said 3.14. It's still in radians. Pi is still 3.14 radians. I didn't ask you what is the numerical value of pi. I asked you what hertz does pi radians correspond to?
Oh,
Y'all are whatless. Whatless. Pi is the highest digital frequency. What is the highest analog frequency? Pi is the highest digital frequency. What is the highest analog frequency? You were taught this. You were taught this in the first class. No, maybe the second class. You were taught this in the second class, and we've been using it all throughout the semester. And yet, when you need to know it, you can't tell me what it is. Fs divided by 2. We said that a million times. A million times. The highest analog frequency is Fs divided by 2, 750 hertz. All right, and so mag analog equals 1 dot divide square root of 2 times pi times f, okay, dot divide by the cutoff frequency. Well, actually, omega c, so I can just use f here. F divided by 1500 dot squared plus 1 close bracket for the square root. And close bracket. Actually, I don't need this first bracket. And let's see if I plot that right. And I use, that's comma there, isn't it? I think it did the same thing here. And so I plot F comma mag analog. And let's save this. And then get rid of the M. Get rid of oh, edit. And then we open it. And there it is. That's the magnitude response. And why give me a second. Something wrong with that, isn't there? Put it on so we can tell. Okay. Okay, what's wrong with that? What's wrong with that? Oh, it's 2000. $1,500 sampling frequency. So that ain't right. It was 2000. 2000. Save this.
Check the next graph.
Excuse me?
It might be the next graph.
What does that mean, the next graph? Where do you have two graphs?
You see how you just pulled up like two tops came up just now when you hovered it over the octave icon?
Yeah.
I was saying you could have checked the next one. I know. Oh no, never mind.
Yeah.
Sorry.
All right. The cutoff frequency, I'll get this right. The cutoff frequency is 2000 rads a second. So that's 318.3 hertz. Okay. So all right. Now, how can we tell this is right now? How can we tell if this is right now?
We could tell because at 70% of our maximum magnitude, you should get the 300 and something hertz.
No, you'll
Yeah.
get, yeah.
Yeah, so there it is. 319. See there in the lower left corner? Okay. 319 hertz at 0.704. So we got the cutoff frequency we wanted. This is truly the analog magnitude response. Okay, now let's plot. Let's plot the digital. Okay. So for the digital, we need to convert F to ohms. How do we do that? So how do we do that? For each F value, what's the corresponding digital value? I must have done this at least twice a day, folks. I must have done it at least twice. What is the relation? What is relation?
2 pi f divided by 1500.
Thank you very much. 2 times pi times f divided by 1500. So the highest value of that should be is pi. Yes, because the highest F is 750, yes. And so now we go to mag digital. my digital equals what? We just derived it. All right.
You have the plus sign?
Excuse me? Oh, I have plus sign. Equals, right? 0.4 times square root. Square root of what? Square root of cosine of omega plus 2 plus 1, okay, dot squared plus sine of omega, okay, dot squared square root. That's the top, not the bottom. Okay. Dot divide. And the bottom is what? Square root. What did I just do?
You type it in the line 25.
Okay. Dot square root. Square root of what? Cosine of omega minus 0.2 dot squared plus sine of omega, okay, dot squared, close bracket, semicolon. Okay. So plot, go down to plot, again, F, comma, my digital. Yeah. Oh, okay. And we go save. All right, error, what error? Line 28, false error. All right, let me see here. 4 square root. Oh, I need another bracket because that's the square root. I need another bracket for the square root. Save. Still got it wrong? Okay, open. That bracket goes with that bracket. All right, so not that one. I don't need that one. But I need that one. Let's hope that's right now. Holy sh! All right. Let me do this in stages.
Did you forget the bracket after the square root sign for the denominator?
I thought I put it in. Okay. Oh,
Right in front now.
I need one there, yes. Okay. I should have done this from the break. I should say numerator equals. Yeah, then I can read it better. All right, so is that right? And denom equals. Dang, I'm running out of time. So equals numerator. Denominator. Now I'm still gonna have an error, but hopefully it'll tell me in which line. So it's the denominator problem. Okay. It's the denominator problem. And where do I have the problem?
How many brackets?
At the end, right? Oh, no.
Yeah. So this bracket goes with that bracket. This bracket goes with the end.
Yeah, let's move that last bracket and try it again. See what
So
happens.
you see the bracket by the two, the extra bracket by the two. Double check that. I don't think I'm supposed to be done.
Because they ain't matching up with the numerator.
Yeah, the numerator. It ain't look the same.
That's right. Yeah,
Okay, let's try it.
yeah, that should work now. File save. Okay. There it is. And lo and behold, let me do one more thing.
What's the labelity?
Yeah, I'm gonna do legend. So legend. The first one I have is what? Analog. Analog.
If you put it there, okay.
Second one is digital. Save file. All right. So the red is digital, and the blue is analog. But unfortunately, they don't have the same cutoff frequency. But I was expecting that. I was expecting that. And I'll tell you why in a second, but let's verify they don't have the same cutoff frequency. So we already verified the color frequency here. That was 318. 318. Okay, 0.709. So right there is the cutoff frequency. Okay. But the cutoff frequency for the digital, okay, 0.7, 0.7, it's 287. 287 hertz. So I did not achieve what I wanted to achieve. I did not achieve what I wanted to achieve. Okay. I'll tell you next class what I have to do to fix that. And if you can't wait till next class, when's next class? Today's what? Wednesday?
So next week, Monday. Okay, like,
So yes, and if you can't wait, read the book. I'll even give you the page. Okay. Page 393. What I just did was example 10.3. And 10.3 has exactly what I gave you. To fix this problem, we have to do example 10.4. There is a fix for this problem. And I've run out of time because I wanted to show you how to plot these graphs. I was just going to show you the picture in the book. See, here's the picture in the book.
You can see your off the screen.
Yeah. Give me a second. Here's the picture in the book.
Hey, Dr. Cutter, the picture at the top, similar like the graph we get.
It is the same.
Cutoff
This
frequency.
the bottom graph here, digital filter. That's ours. The analog filter, that's up top here. The middle graph is the fix. That's how you fix it to get the same cutoff frequency. You see those two have the same cutoff frequency? And that's called a pre-warped digital filter. And I don't want to rush through it now. I want to take this time to go through that on Monday. But if you can't wait, read example 10.4. Any questions before we go?
Dr. Carter, I see we only have 2 more classes left for the semester. That's correct?
Only what?
2 more.
How do you figure that?
And we take an exam Wednesday, right? Week after next Wednesday.
We got the 13th, we got the 15th, we got the 20th.
You having class on the 20th?
Why can't we have a class on the 20th?
When are you supposed to study?
Young man, you're supposed to be studying all semester. I keep telling you all that. I ain't telling you we won't have 20 off, but I ain't telling you will either. It depends how far I get on the 13th and the 15th. You cannot count on 2 days of using classes for exams. I've been telling you all semester you must study after every class. Any other questions? Okay. See you on the 13th, Lord willing.